So seating chart's up. Go ahead and make sure you do your seating chart if you haven't already done so. Please make sure those masks are covering noses and mouths. Mask covering noses and mouths, please. In the back. Noses and mouths, please. So y'all ready for Thursday? Nobody ever is. It's okay. You just do the best you can. It's okay. Always just do the best you can. Never leave anything blank, right? Always put something on the exam and the answer sheet. Always put those answers on the exam too. Did we talk about that when I gave back exams? Somebody had missed transferring. If you leave it blank on the answer sheet, some people do that, like they'll go back to a question they skipped, right? And they go back on the exam, but they forget to go back and put it on the answer sheet. I will actually go back and I will check your exam. If you have a blank answer on your answer sheet, I will go in and look on the exam and see if you wrote an answer on the exam. So it's in your best interest to put your answer on both the exam and the answer sheet, just in case. So don't forget to do that. Sometimes that 2 points means the difference between a letter grade, you know? Okay, so we got 1 more minute. Oh, I think I forgot to tell last class a joke. I think I did. Okay, so why are fish easy to weigh? Because they have scales. How does a whale protect himself? With a swordfish. It's good stuff, good quality stuff. Okay, so make sure that you've entered your name on the seating chart. All right, there are a few things that I added. In chapter 6, y'all had asked for me to go over the very end of the reducing sugars. So I did that. And then I also added in chapter 7, we'll talk about it quite a bit today, but I added at the very end, go all the way down, I added this animation on how water dissolves salt. We're going to talk about it a lot today, but sometimes seeing an animation is really helpful. So that's in there if you want to go and watch. It's like 2 or 3 minutes, it's not long. Okay, so today we are going to do our problems first, and we're going to do eye clicker last. So we're going to switch things up, but make sure you have your eye clicker because we're going to do some. We will be doing some. All right. So last time we were talking about all kinds of different intermolecular forces, right? So before we answer 7.24, I want to talk about what those intermolecular forces are that we discussed, right? We discussed London forces. Sometimes you'll see them also as London, and this is what I say, is London dispersion forces, or LDFs. It's the same thing. All 3 things are the same thing. London dispersion, London forces, London LDFs. It's the same thing. So London forces, remember, are those temporary dipole moments that happen when things collide. So what kind of molecules have London dispersion forces? Everything. Non-polar molecules have it. Polar molecules have it. Ionic compounds have it. Covalent compounds have, everybody's got it. Everybody. If they ask what forces are present, if I ask what forces are present, you have to say London dispersion. Then you look at the molecule and see what else is there. Okay. Dipole, dipole. What happens? How do you get dipole-dipole interactions? You have to have two molecules that both contain a dipole, right? So water with itself, are you going to have an interaction? Is water polar? Yes, it is. So if you have two polar water molecules interacting, you will have a dipole-dipole interaction. But that's a special kind of dipole-dipole interaction. Why is it a special kind of dipole-dipole interaction? Because it's hydrogen bonding, and hydrogen bonding is stronger than regular dipole-dipole interactions. How do you know if you have hydrogen bonding? You look for hydrogen bound to no fun, nitrogen, oxygen, or fluorine. That's how you know if it's hydrogen bonding. Okay, how do I know if I'm going to have an ion dipole interaction going on? What is the difference between something that's an ion and something that has a dipole? It has a full charge, at least +1, at least -1, could be a +2, could be a -3, right? Could be any number as long as it's a whole number. Dipoles are partial charges, right? So ion is like a +1, a -1. A dipole is the sigma plus, the sigma minus, because that means partial, right? What about ionic? That's a plus and a minus, right? Full positive, full negative. Okay. So knowing these things, we're going to be able to predict so much about molecules and how they interact. So in order to do that, we kind of have to know what functional groups are actually going to carry ionic charges. Like which ones can participate in ionic interactions or ion dipole interactions. So which functional groups that we know of, which ones contain ionic charges? Let me give you a hint. What's a carboxylic acid? I wanted to draw a carboxylic acid. What would I draw? R bound to a carbon, double bonded to a oxygen, OH. That's a carboxylic acid. Does this have a charge? Did I just lie to you? No. But what happens if I take away that hydrogen? Does oxygen now have enough bonds? No. So instead of only having 2 lone pairs, it now has how many? 3, which means it carries a negative charge. So when I lose that hydrogen, it gives the oxygen a negative charge. And then we no longer call it carboxylic acid. Now we call it carboxylate. Okay, so this is one of them. Anybody know the others? They're a group of amines. What are amines? Nitrogen containing, but they're a particular kind of amine. They are protonated amines. So do you see how in the carboxylate, we took away a hydrogen and we got a negative charge? What do you think is going to happen for an amine if it's protonated? A proton is like a hydrogen. We're going to put an extra. So if I put a nitrogen, I want a primary amine. How do I know it's primary? I have how many R groups? Only one. It refers to R groups, not hydrogens. So we have one R group. If it's not protonated and it's uncharged, how many hydrogens are attached to this nitrogen? It would be NH2 is the non-protonated version, but I want the protonated. So I'm going to give it 3 hydrogens. Because I gave it an extra hydrogen, it now carries a +1. So all protonated amines are going to carry a +1. So what if I had a secondary amine? How would I draw that one? R 1, 2, or 3? 2. Bound to a nitrogen. Bound to, can we still be bound to 3 hydrogens? No, now we need to be bound to 2 hydrogens to carry a +1 charge. If I had a tertiary, and we could keep going with this, but we're not going to, this would be the last one we do. We would have a R3, still bound to a nitrogen, still bound to 1 hydrogen, and that would be a plus. Okay. Yeah. All right. So now we know all of our forces. We know some things that can be positive, that can be negative, right? So now we need to start applying that to molecules. So let's look at A. What we need to do is we need to identify the strongest attractive force present. So in order to do that, I'm going to ask you for each force, yes or no. And once we answer that, then we're going to pick the strongest that was a yes. Okay. So look at A. This is what kind of a compound? We have lots of carbons and hydrogens, no double bonds. So we have an alkane with what kind of a functional group? A hydroxyl, right? An OH. So we have an alcohol. AlCOHOL. Alcohol, hydroxyl, right? However you want to think about that. So tell me about things that have an OH, right? I'm going to say R, and it's going to have OH, and we have 2 lone pairs. What does that kind of look like to you? Kind of looks like water, right? So tell me about things that have hydroxyls. What kinds of interactions can they participate in? Hydrogen bonding. We have a donor here, and we have 1, 2 acceptor sites. So the question is, identify the strongest attractive force present in pure substances. So do we really have water going on here? No, it's a pure substance. But this is similar to water in that I can have another molecule, right? So I'll just draw the same exact thing, H bonded to O, bonded to an R group. Now what I can do is I can have a hydrogen bond form between the acceptor site on the blue molecule and the donor site on the red molecule. That's a hydrogen bond. So anything that has a hydroxyl can hydrogen bond with another molecule of itself. Okay, so let's go down our list. Do we have London forces? Does it exist? The answer is yes. Okay, you're always going to say yes to that one. Do you have dipole-dipole interactions? Do your molecules have a dipole? Does water have a dipole? Yes, this is really similar to water. Yes, it has a dipole. Are those dipole-dipole interactions extremely strong in that they are hydrogen bonding? Yes, they are. So if you have hydrogen bonding, you have dipole-dipole interactions because it is a type of dipole-dipole interaction. Okay, ion dipole. Do you see anything that has a fully positive or a fully negative charge? No. So we don't have an ion. So then we don't have ion dipole. Can we have ionic? No. Okay, now, which is the strongest attractive force present? Hydrogen bonding. Okay. Yeah, questions? Okay. So what did we not draw on these molecules? We didn't say this is partial positive. This is partial negative. This is partial negative. This is partial positive. But those partial charges are there, right? Because we said they are polar. With me? Okay. So let me erase this and we're going to start again because I need room. I'm running out of room. Well, that's a terrible sound. Okay. B, KCl. Tell me about KCl. This is an ionic, ION. This is an ionic compound. So really what's there is a positive one for potassium, potassium. And then chlorine is in group 17, 7A. So it has a -1. So what kind of interaction is going to happen? Well, I'm going to have another Cl minus here. I'm going to have another K plus here, right? I'll have another K plus here, another Cl minus here. Have you ever seen an ionic compound as this grid, right? This lattice work. So each one of the atoms is attracted and stays in this grid because they're all attracted to one another. All the positives are attracted to negatives, all the negatives are attracted to positives. So let's go through our list. Do we have London forces? Yes. Do we have dipole-dipole interactions? Did we draw a dipole? So if we don't have dipole-dipole interactions, can we have hydrogen bonding? Absolutely not. If we didn't draw a dipole on anything, can we have ion dipole interactions? No. What do we have? Ionic. So we have ionic and we have London. Which one is the strongest? Ionic. Okay. All right, now C, CH2, Cl2. Draw the Lewis structure of that molecule for me right now. Carbon in the middle. Really, it's one of these bonds is going downwards, right? We'll give chlorine all of its lone pairs. All right. So do we have London forces? Does it exist? Yes. Do we have dipole-dipole interactions? The question is, do we have a dipole? So if we look at this molecule, in order to have a dipole, we need to have, number one, polar bonds, and number two, an asymmetric molecule. Do we have polar bonds? How do we know if something is a polar bond? Differences in electronegativity. Where could you go to find differences in electronegativity? Go get your best friend. Go get your best friend right now. Your best friend has a table of electronegativity values. Is there a difference in electronegativity between carbon and hydrogen? Technically, what? Yes, there is. But what do we say about that bond? That electronegativity difference is so small that we pretend like it doesn't exist because it really doesn't impact the molecule. Okay, so all carbon hydrogen, we say it's nonpolar. How about carbon and chlorine? Do we have an electronegativity difference? Oh, absolutely, we do. Which one's more electronegative? Chlorine. And I can just look up on the periodic table, who's closer to fluorine the floozy? Chlorine. So chlorine is going to be more negative. So I'm going to give this bond a polarity. So all the carbon chlorine bonds have polarity. If I combine all of these bonds, do I have an overall dipole moment on my molecule? I do. It kind of goes like this. So yes, I have a dipole. This is a non-polar molecule. You remember when you had to figure that out? Do you remember whatever, I don't remember what chapter that was. 4, 5, 4. You had to look at molecules and say, are they polar or not? This is why it was important. You're applying that now, right? So we have a non-polar molecule. That means that we have a dipole. So if we took one of these molecules and I copied and pasted it, and I pasted this exact same thing right next door, would one interact with the other? Absolutely, because I have a partially positive side and a partially negative side, right? That makes this chlorine partially negative, and it makes this side of the molecule partially positive, right? That's what this arrow means. So do we have dipole-dipole interactions happening? Absolutely, we do. Do we have hydrogen bonding? I see hydrogens, but what's the rule? Hydrogen must be bonded to nitrogen, oxygen, or fluorine. No fun. It's no fun. Is hydrogen bound to nitrogen, oxygen, or fluorine? No. So do I have hydrogen bonding? No. Do I have ion dipole? Do you see an ion? No. All of these are partial charges. So there's no ion, so there can be no ionic. So what is the strongest charge that is happening in C? The strongest interaction that's happening in C? Dipole-dipole. Okay. Now D. D's already drawn for us. It's very nice of them. Polar or non-polar? Is there an electronegativity difference between oxygen and carbon? Yes. And this oxygen actually has 2 lone pairs on it. Remember, if oxygen has 2 bonds, it has 2 lone pairs. So is this a polar molecule? Absolutely it is, because this bond here is polar. So then we have an overall dipole moment of this. We have a partial negative here. We have a partial positive here. So do we have, oh, I got to erase over here. Let's start from the beginning again. Do we have London forces? Yes, we do. The molecule exists. It has London forces. Dipole-dipole. Do we have dipole-dipole interactions? If you can draw a dipole, you have dipole-dipole interactions. So yes. Do we have hydrogen bonding? No. We have 2 acceptor sites, but do we have a donor? There is no donor, because this is a pure substance. It's not in water. If you put it in water, then the answer would be yes, but it's a pure substance. It's not in water, so we don't have hydrogen bonding. Do we have any ions? So can we have an ion dipole? No, no ion. And no ion means no ionic. So what is the strongest force present? Dipole-dipole. If you find something that is non-polar, why did I say non-polar? If you have something, it's polar, that's a polar molecule. Y'all scratch that out. Why did I write that? Because I was talking and writing at the same time. So if you have something that's a polar molecule, it has a dipole. Therefore, it can interact in dipole-dipole interactions. If you find a molecule that is completely non-polar, so what if I had something like this? I just removed my functional group that has polarity. Now I have a fully what? Non-polar substance. What is the only force present? London dispersion. Okay, so if you do this, this is non-polar. You have to scratch out the hydroxyl and you have to put extra hydrogen on there. That would be non-polar, and the only one would be London dispersion forces. Okay. We just didn't see an example like that in here. Okay, now that you know how to identify things as to whether they're participating in different intermolecular forces, now you have to be able to draw those intermolecular forces. So you have a molecule of CH2O. How do you draw that? Carbon, give that carbon some hydrogens. And then I have an oxygen, right? Anybody happy in this? Just hydrogen. Hydrogen's cool, but carbon's not happy and oxygen's not happy. So how do I fix this? Give them a double bond. Okay, now carbon's happy. Oxygen is still unhappy. We need lone pairs. How many lone pairs? 2. Okay, now remember, this is kind of our molecule towards the top. You can go up, right? Right here. It's the same molecule in D. So D said we can have dipole-dipole interactions, but was there hydrogen bonding? No, but that's in the pure substance. So when you come down here, it says how many hydrogen bonds can this molecule make to water? So this oxygen right here is partially what? Partially negative. This side of the molecule is partially positive. So we can draw our dipole moment like this. So if you have something that's partially negative, what is it going to want to interact with on water? The hydrogens or the oxygen? Because why? They're partially positive. So I'm going to draw my hydrogen close to my molecule, right? And I'm going to say, okay, here is a partially positive hydrogen, a partially positive hydrogen, and a partially negative oxygen. So we have an overall dipole moment going like this. So where does my hydrogen bond occur? Between a hydrogen that is bound to an electronegative element. This is the donor. And then that can interact with an electronegative element. So each of the lone pairs can provide an acceptor site. So I draw my hydrogen bond here as a dashed line. Can this CH2O make another hydrogen bond with water? Sure, where? The other lone pair is also, I want to do it in the same color, is also, same color please, an acceptor. Okay, so I'm going to draw another hydrogen bound to an oxygen. And that hydrogen is partially positive, oxygen partially negative, right? We have this overall dipole moment. And so we can have this hydrogen bond occur between the oxygen on the CH2O and the hydrogen on water. So this is another donor here. Okay, can CH2OH make another hydrogen bond with water? No. This hydrogen, can it act as a donor? Is it bound to no fun? No, it's bound to a carbon. So it can't. This cannot be a donor hydrogen. If it were bound to another oxygen, a nitrogen, or fluorine, then yes, but it's not. So how many hydrogen bonds can CH2O make with water? 2. All right, now we've talked about intermolecular forces. What do intermolecular forces tell us? Like, they're really cool, but what do they tell us? They tell us the physical properties of substances. So I want you to write this on your paper. The stronger the interaction, or the more interaction you have. And what do we mean by interaction? We mean intermolecular force, or the more of one intermolecular force you have, you're going to have an effect on 3 things. On boiling point, on melting point, and on vapor pressure. Now this, I am not going to give you. This is not on your best friend. So what do you think you should do with this? I would memorize this And let's talk through it, because once we talk through it, you're going to understand it. So think about this. If you have a substance that has a very weak interaction with other molecules, it's going to be very easy to overcome that interaction and change phases. So let's talk about water, for example, right? Why are we mostly water? We are actually mostly water. And the reason is that we have really strong interactions between water molecules. What interaction is that? Hydrogen bonding, hydrogen bonding. So it takes a really high temperature to convert that water from a liquid to a gas. So that's what boiling point is, converting from a liquid to a gas, right? So we take the liquid, we boil it, we turn it into a gas. What do you put in your car to keep your engine from overheating? Coolant fluid, right? Antifreeze coolant. Why? Because it's mostly water. It's going to absorb lots of heat before it turns into a gas. It's going to keep your engine cold. High melting point. So melting point is the point at which you turn from a solid to a liquid. So if your boiling point is high, you have lots of really strong interactions. Same thing is true about melting point. If you have lots of interactions, it's going to take a higher temperature to convert you from a solid to a liquid. That makes sense, right? Okay, vapor pressure is different. Do you notice how vapor pressure is the opposite? So what is vapor pressure? If I have a water bottle, right, and it's at room temperature, there's a small portion of the liquid that's in that water bottle that will actually turn into a gas or a vapor, right? Vapor, gas, same thing. So that gas in the top of that water bottle will actually exert a force on the surface of the liquid and on the sides of the container. What happens if I heat that water bottle and the water bottle doesn't melt? More liquid turns into what? Gas. If I keep heating it, what is going to happen to that bottle? It's going to explode. It's going to explode because the pressure got so high, right? It exploded. That's vapor pressure. So if you have something that has a very high boiling point, it's going to be really hard to transition that from a liquid to a gas. So in that sealed container, are you going to have very much gas? No, most of it's going to be in a liquid form. So if you don't have a lot of gas, do you have high vapor pressure? No. So boiling point and vapor pressure are inverse of one another. Sometimes, this is what I recommend. When you get your exam, some people do this. They take their exam, they flip it over to a blank spot, and they just start writing some things, right? Things you know, things that you know I'm going to ask you on the exam. This would be a really good thing to write. Yeah? Okay. So let's try to answer some of these. Predict which pure substance would have the lower melting point. I know it's hard to read, but the lower melting point. Baking soda, NaHCO3, or phenol, explain your answer. I don't try to just answer that right away. I try to look at the molecules, and I know that boiling point, melting point, vapor pressure are all dependent upon intermolecular forces. So let's go in and see if we can identify the intermolecular forces present in each of the molecules. So NaHCO3, I know it says baking soda, but I want to name that properly. How do I name that molecule? Is it monosodium, monohydrogen, monocarbon trioxide? Does that make sense? No. No. So how would I name that? Sodium, I heard somebody starting to say it. Sodium bicarbonate. What's another word for bicarbonate? You could have named it sodium bicarbonate or sodium Hint, hint, it's in your best friend. Where are you going in your best friend? Polyatomic ion table. So there are two different names for HCO3. Hydrogen carbonate. Either one is correct. So what kind of a compound is this? I have this sodium is what kind of an element? It's a metal. What is bicarbonate or hydrogen carbonate? You got it from the what kind of table? Polyatomic ion table. So what kind of a compound has a metal and a polyatomic ion? An ionic compound. So this is an ionic compound. And that ionic compound has what is the strongest intermolecular force? Not the only, but the strongest intermolecular force. London dispersion, it's there, but it's not strong. Dipole, dipole, we don't have a dipole. We have ionic, right? Ion dipole, no. What do we have? Ionic. So this is ionic, I'll just say intermolecular force. Okay, let's do the same thing with phenol. Phenol is C6H5OH. Carbon and hydrogen, right, that's nonpolar. What about that OH? It's an alcohol because it has a hydroxyl. So tell me about intermolecular forces and alcohols or hydroxyls. What can they do? They can hydrogen bond. Bonding as its intermolecular force. Okay, so which one has a stronger intermolecular force? What's stronger, ionic or hydrogen bonding? Ionic, so this is stronger, STRONGER, stronger intermolecular force, stronger intermolecular force. So go up to your little thing. What does my little thing say? Stronger interactions, higher boiling point, higher melting point, lower vapor pressure. So which one is going to have the lower melting point? If I want low, let's do it this way. If I want low melting point, am I going to have strong interactions or weak interactions? Weak intermolecular forces. Oh, I said both are stronger. Which one's stronger? Ionic is stronger. Why did I write stronger? Weaker. Right? Okay, so which one has weaker intermolecular forces? The phenol or the baking soda? The phenol has weaker intermolecular forces, so we'll have a lower melting point. This builds and builds and builds. So if you discover you have a gap somewhere, come get some help. Absolutely come get some help. Okay. Now, we're going to do the same thing with this, but we're going to rank the following compounds in order of increasing boiling point, lowest to highest. So the lowest boiling point will be 1, the highest boiling point will be 3. Okay? So let's look at each of these molecules and let's see what we can do with it. That very first molecule, where's that functional group in there? You might remember it as this. What is that? It's an ether. It's an ether. So actually that oxygen has 2 lone pairs on it. So if you want to add that, you can. But this is an ether. What kinds of interactions can happen with an ether? It can accept hydrogens, but there are no hydrogens to accept. Right? This is a pure substance. We have no hydrogen bound to a nitrogen, oxygen, or fluorine. So can we have hydrogen bonding? No. What could we have? Do oxygen and carbon have different electronegativity values? Yeah. So what can we have? Dipole-dipole. So this is a non-polar molecule. So we can have dipole, dipole interactions. Okay, how about my next molecule? What kind of functional group do I have? I have an alcohol. Al. Oh, oh, oh. So we usually call the functional group the hydroxyl, and then we call the molecule that contains the hydroxyl the alcohol. But I don't care that you know the distinction, just that they kind of mean the same thing. Okay, so if I have an alcohol, what can happen with an alcohol? We can have hydrogen bonding. That's something that you should automatically just see alcohol, oh, hydrogen bonding, right? H bonding. Okay, how about my last molecule? Do I have any functional groups? So what is this molecule? This is non-polar. If I have something that's non-polar, what is the strongest type of intermolecular force I got? Those poor-saddled London dispersion forces. Okay. So tell me about boiling point and strength of intermolecular force. I want to start with something that has the lowest boiling point. So low boiling point is going to mean what?
Would it either be a polar molecule?
It is because at that oxygen, it's not symmetric. It's bent. It's a bent molecule. It's not really straight. Oh, yes. It's a polar molecule. Sometimes I say one thing and I write something else. You're right.
I was just wondering.
You're right. You're absolutely right. You can't have a non-polar and have dipole-dipole. Yeah, sometimes I'm just, in the moment. Okay, so if I have low boiling point, what is that? What is true about intermolecular forces? Do I have strong intermolecular forces or weak intermolecular forces? Weak. And then if I have a high boiling point, what do I have? Strong. So what I'm trying to go is from my lowest boiling point to my highest boiling point. So I'm in essence going to go from my weakest intermolecular force to my strongest intermolecular force. So let's rank these. Give me a ranking for each one. Which one should the ether be? 1, 2, or 3? 2. What should my alcohol be? 3. 3 is the strongest. Hydrogen bonding is stronger than dipole-dipole. Dipole-dipole is stronger than London dispersion. So London dispersion is the lowest, the weakest intermolecular force, so therefore it has the lowest boiling point. Then ether, because it's a dipole-dipole, then hydrogen bonding. Yeah? Okay. Okay. We have 2 common inhalation anesthetics, desflurane and halothane. They both have boiling points. The desflurane has a boiling point of 23.5. So let's write that. Has a boiling point of 23.5 degrees Celsius. And then halothane has a boiling point of 50.2 degrees Celsius. Which one is predicted to have the higher vapor pressure at a given temperature? I'm telling you, write that little thing. Stronger or more intermolecular forces, what do you get? High boiling point, high melting point, and low vapor pressure. Okay. So which one is predicted to have the higher vapor pressure? So high vapor pressure would mean what? Lower boiling point, because they're inversely related. So the one with the higher vapor pressure has a lower boiling point. Which one has the lower boiling point? Desflurane has the lower boiling point, so it has a higher vapor pressure. Write that little thing, write it down. It will help. Okay. Now, we can use the intermolecular forces that we know about, and we can make predictions about what molecules are going to do in certain situations, right? So have you heard like dissolves like? Heard that before? Okay, so why does salt dissolve in water? Salt is ionic, water is polar, so they're both either charged or partially charged, so they're attracted to one another, right? That's the like. How about oil and water? That's insoluble, right? That will not mix. If you have your salad dressing, right? What happens when you leave it in the counter or leave it in the fridge? It separates. You have to shake it up before you put it in your salad, right? Same thing if you're boiling a pot of water. You put a little bit of olive oil in there, and what happens to the olive oil? Makes those little pools on the top of your water, right? They don't mix. Why don't they mix? It's oil, right? And oils are a type of fat. Remember when we drew fat? What happens with fat? Right? For example, fats are fatty acids. How would I draw a fatty acid? An oxygen, carbon, right? You start with this, yeah? So we lose our hydrogen and our oxygen picks up a negative charge. Remember this? Yes, possibly. So we have a polar area and we have a huge non-polar area. So this big non-polar area does not want to associate with water. It will actually form a micelle in order to stay away from water, right? It always makes what shape? If you drip oil into your pot, what shape does it make eventually? I mean, as it's moving, if it's boiling, it's moving and stuff, but what does it make? It makes circles. Why does it make circles? What's the shape of a micelle? It's a circle. You have all these little polar head groups and then these fatty acid tails, polar head group, fatty acid tail, polar head group, fatty acid tail, right? What shape? Circle. It's a circle. This is how soap works. Soap, you actually have a salt of a fatty acid, and you have like this little particle of dirt in the middle. This is dirt. And dirt is non-polar. So the non-polar dirt wants to associate with the non-polar fatty acid tails. And so it creates micelles and you wash things down the drain. So everybody who's spending lots of money on that micellar water, you know what's in there? Can water form a micelle by itself? No, it can't. So there's some oil in there, right? That acts like soap and washes the dirt off your face. That's all it is. So the actual brand name is a lie. It is not micellar water. It is water that contains my cells. You cannot physically have micellar water. It's crap. Okay, so there was my little side note. Okay, NaCl, is this going to, based on its polarity and attractive force, is it going to be soluble, insoluble, or form a micelle in water? Salt, this is in your cabinet. You pull it down, shake some into a glass of water. Does it dissolve? Yes, it dissolves. Okay, so this is soluble. But let's chemically think about that. Because I'm not going to give you an NaCl on the exam. I'm not. So what about NaCl makes it soluble in water? It's an ionic compound. An ionic compound. That ionic compound can have ionic interactions, ACT, interactions with itself, and what can it have with water? Is water an ion? No, so what can it do with water? Ion dipole interactions. Yeah, because water has a dipole moment and the NaCl are ions. So with water, because that's what we're saying, in water. Okay, sodium stearate, a fatty acid salt. I just drew above a fatty acid. So what's a fatty acid salt? I take away that hydrogen, so I don't have a hydrogen, so I have a charge on that oxygen, and then I put it in association with a metal. Now I have a fatty acid salt, because I have a positive and a negative. So tell me this sodium stearate, a fatty acid salt. Now this isn't really sodium stearate because this 18 tells you the number of carbons. So I would have to have 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 7 more carbons in this chain to make sodium stearate. What's the 0? No double bonds. Means no double bonds. Okay, so we've drawn our molecule basically. What kind of interactions can it form with water? You can have ion dipole with water, but can the whole molecule have ion dipole? No. The head group, so the head group has ion dipole interactions with water, but the tail is very nonpolar, very, very nonpolar. So what's the tail going to do? It's a micelle. We'll create a micelle. Yeah, micelle. So the question is it going to be soluble, insoluble, or form a micelle? So if it forms a micelle, technically it's not soluble. So what I've drawn over here, this micelle that I've drawn over here, really you have water associating with it, right? You have the hydrogen, oxygen, hydrogen, hydrogen, oxygen, hydrogen, right? So these head groups are interacting with water, sure. But this is not soluble because you have a micelle. So you can't be soluble or insoluble. You just form a micelle. It's like a hybrid sort of thing that we say. Okay. So A was soluble, B is a micelle. How about C, isopropyl alcohol? Think about it logically. Before you do all the chemistry, think about it logically. Have you gone to the store and bought 70% alcohol? Sure, that's rubbing alcohol, right? What's the other 30%? It's water. Do you see a layer? So is it soluble? It is soluble. Like, you can use logic sometimes, but now we need to explain it based on polarity and attractive forces. Isopropyl alcohol has what? It has a hydroxyl. So it is an alcohol. If it is an alcohol, what can it do with water? Hydrogen bonds with water. That's what makes it soluble. If you ever wonder why some things are soluble and some things are not, this is it. We say that like dissolves like, but that doesn't really explain why. It's a good rule of thumb, but it's not an explanation. Now you really know. Isn't that awesome? So if you want to see salt dissolving in water, like the animation of physically how the atoms interact, I posted that video in chapter 7, at the bottom of chapter 7. It's really good. Okay, next page. Okay, predict which of the following compounds is likely to be more soluble. Okay, more soluble. So look in A. Tell me about that first compound in A. What does it have? It's an alcohol. It has a hydroxyl. So this is going to be able to participate in what? It can do hydrogen bonding with water. How about my second compound? That's a saddle nonpolar molecule, right? Is it going to interact with water? No, this is insoluble. This is insoluble. So which one is likely to be more soluble in water, first or second? First one. Okay, look at B. What do you think, first or second? So I'll kind of erase that. Okay, so let's draw them. That first one, I have a nitrogen in the middle. The nitrogen is bound to 2 hydrogens and a CH3 molecule. Is that nitrogen complete its octet? Or does it need a lone pair? Okay. I'm going to draw H2S. Is sulfur's octet complete? Nope. Okay. What can the first molecule do with water? We can have hydrogen bonding because I have this acceptor site, I have this donor, and I have this donor, right? So I can make 3 hydrogen bonds. Okay, what can SH2 do, or H2S, doesn't matter. What can it do? No, it can do something. It can do something. Can it hydrogen bond? No, we don't have a hydrogen bound to no fun. But is there an electronegativity difference between sulfur and hydrogen? Yes, there is. So we actually have dipole moments in here. So what can we do with water? Does water have a dipole? Yes. Does this molecule have a dipole? Yes. What can we have? Dipole interaction with water. So this is hydrogen bonding. Okay, so which one is more soluble? Are they both soluble in water? Yes. which one is more soluble in water? My first one, because it can participate in stronger interactions with the water. I've got this. Okay. What component molecules make up a triglyceride? What is a triglyceride? Well, what does tri mean? 3. And it refers to 3 fatty acids. And glyceride refers to glycerol. So what component molecules make up triglyceride? 3 fatty acids and a glycerol. But I feel like you kind of need to see that, right? What's a glycerol? It's 3 carbons in a chain, and each carbon has a hydroxyl. Now, does that first carbon have a complete octet? No, he's not really happy. How many carbons does he need? How many carbons? How many hydrogens does he need? 2. The second carbon, how many hydrogens? 1. The third carbon, 2. So this is a glycerol. Okay, so now to that glycerol, I want to add 3 fatty acids. What is a fatty acid? I have my hydroxyl bound to a carbon, right? And that carbon's a carbonyl carbon. And we have some length of tail, it doesn't really matter, right? So I'm going to do that 3 times, right? I'm going to go right, same thing. Okay, so I have 3 fatty acids. This is my 3 fatty acids. This is my glycerol. Glycerol. I'm going to add these together. How do I do that? How do I add them together? What do you notice? What kind of a reaction could I do? A condensation, I could yield water and some of my product, right? So let's draw what my product is going to be. So what do I have to do to make water? I have to take away a hydrogen and a hydroxyl, or a hydroxyl and a hydrogen. Right? It doesn't matter which one I take it from, so long as I pull out 2 hydrogens and an oxygen. So what am I left with if I do that for all of my molecules? All I'm going to have to do now, let's see if I can do this, is link the 2. Will it let me do it? Pull it over and link it, right? Same thing. Oh, it's not going to like that. Pull that over, and I've created, of course, a triglyceride. So plus water, right? And a condensation condensation. Yeah, so it's 3 fatty acids plus a glycerol. CEROL. Make water in a condensation reaction. So we get a triglyceride in water. Okay. All right. So you remember when we talked about different kinds of fats? We talked about trans fats and cis fats. You remember that, right? Where those fatty acids, where the hydrogens were on that carbon-carbon double bond. Okay. Well, so if I have in my house at home, I have olive oil and I have butter. If I leave them both out on the counter, how do they look? What state of matter is oil in? It's a liquid. What state of matter is butter in? Why? They are both fats. One's saturated, one's unsaturated. What's what? Butter is saturated. And what does saturated mean? So has max number of hydrogens, max hydrogens. So no carbon-carbon double bonds, right? We have all carbon-carbon single bonds. What about olive oil? Olive oil is a liquid, so it is unsaturated. So it has some number of carbon-carbon double bonds. Why is that important? If you look at butter, butter's fatty acid tails are just like this. And each one lines up perfectly. So do you see how they line up? They're like pages in a book. They are smashed together. The more interaction you have, the more London dispersion forces you have. So butter has a ton of London dispersion forces. Ton of London dispersion forces. Olive oil, on the other hand, is an unsaturated fat. So you might have some chains that don't have anything, but then you're going to have some chains that do. Do you see how now we're not lining up perfectly anymore? Am I perfectly one on top of the other? No. So do I have more or less London dispersion forces? I have less. So the more carbon-carbon double bonds you have, what can we say about London dispersion? Less London dispersion forces. Okay, go back to the little thing I told you to memorize and write down. If I have less London dispersion forces, what effect does that have on melting points? If I have weaker or less intermolecular forces, I have a lower melting point. Okay, let's now read the question. Olive oil is a mono unsaturated oil. What does that mean? It has one carbon-carbon double bond. With a melting point of -6 degrees Celsius, soybean oil is a polyunsaturated fat. So here we have greater than one carbon-carbon double bond. It has a melting point of -16. Explain their difference in melting points. We could use what we already wrote, right? Which one has more carbon-carbon double bonds? Soybean oil. So soybean oil has more carbon-carbon double bonds. Therefore, it has less London dispersion forces and a lower melting point. Does it really have a lower melting point? Yeah, -16 versus -6. Now, both of these are oils. So at room temperature at 25 degrees Celsius, that's room temperature. They're both oils. They're both liquids, right? But they will melt at different temperatures. So olive oil will melt at -6 and soybean oil will melt at -16. Okay. Pretty cool, right? Awesome. Okay. So remember when we saw those designations behind fatty acids? We said, okay, here's the first number is the number of what? Carbons. The second number is the number of carbon-carbon double bonds. But if you have that, then you want to say, where is that carbon-carbon double bond? So this is telling you at carbon 7, omega 7, omega is You know the alpha and the omega, have you heard of that? Alpha is the beginning, omega is the end. So if you go to the end of the molecule, right, wherever your carbonyl carbon, this would really be carbon number 1, right? Y'all know how to number carbons. All your functional groups, that's where you start numbering. But they're saying go to the last carbon, the omega carbon. This is the omega carbon. And count from the omega carbon, which is freaking ridiculous, but okay. We're going to go 1, 2, 3, 4, 5, 6, 7. So the double bond occurs between the 7th carbon and the next carbon, which is carbon 8. So that's why they call it, you've seen that, omega-3 fatty acids, omega-8 fatty, omega-9 fatty acids, all that kind of stuff. That's what that means. Don't you feel so smart now? You know what all that stuff is? Okay. One of the main triglycerides, we know what a triglyceride is, right? In palm oil is tripalmitin. It contains 3 fatty acids with carbon designations of 16-0. What does that mean? I have 16 carbons and I have no carbon-carbon double bonds, or 0 carbon-carbon double bonds. Would you expect this molecule to be a solid or a liquid at room temperature? Well, what does it look like? I'm going to go 1, 2, 3, 4, 5, 7, 8, 9, 11, 12, 13, 14, 15, 16. Okay, so I'm going to take this and I'm going to copy it. And I got a triglyceride, so I'm going to paste it 3 times. And look how nicely that's going to fit right in there, right? And I'm going to paste it again. Oh gosh, it's going to pack in so nicely, right? Look how nicely that packs in. Okay, and each of these has a double bond to an oxygen. And then it comes down to an oxygen. Normally it would be an OH, but we know this is bound to a glycerol. So it's bound to our glycerol. The top one is CH2, H, CH2, right? So what kind of a fatty acid are we looking at here? This is a saturated fatty acid. Would I expect this molecule to be solid or liquid at room temperature? Solid. Because those tails are packing together like that, those pages of the book. So they have lots and lots of London dispersion forces. All right, last thing. Whew. We're going to talk about these interactions and how they relate to things inside the cell. So phospholipids are the most common type of lipid that are found in membranes. Phospholipids, instead of having 3, do you see how this, if we scroll down all the way, oh my gosh. See how we have 3? A phospholipid, basically what you do is you delete one of these. Maybe. I hit delete. I don't know what happened. Did it delete it? No. Why? I can cut it. Ha ha ha. You can cut it. So you remove this stuff, and then I'm just going to swing around the oxygen, and then I bind it to an oxygen, a phosphate. And a phosphate is a phosphorus surrounded by oxygens, but it's negatively charged. So you have a head group that's not only polar, but it's negative. And so this is what happens in your cell membranes. And so what you end up having are these negatively charged polar head groups. They're all negative. That are like, hey, water, let's hang out. You look like fun, right? Your hydrogens are all positive, and I just love that your hydrogens are positive because I'm negative here on the head group, right? So they'll hang out with water. So this is like the exterior portion of the cell or the interior cytosol of the cell. But these fatty acid tails, do they want to hang out with water? Are they soluble in water? Oh, so they hang out with each other. So that's what makes the bilayer, right? So the other thing that's really interesting is how steroids like cholesterol work, right? So you don't have to be able to draw cholesterol. I'm not going to ask you to draw cholesterol. So cholesterol has all kinds of cyclic structures inside of it. And then it has a nonpolar tail, kind of like a fatty acid does. So what do you think is going to happen with a steroid? We have all of these carbons and hydrogens, right? That's what this is. It's carbons and hydrogens. This one's a house, so it kind of goes across. I'm not the best freehand. And we have these long non-polar tails, right? So all of this is carbons and hydrogens. Is this going to interact with water? No, it's all carbons and hydrogens. It's not really going to interact with water at all. But on the end, you have one hydroxyl group. So steroids are a type of lipid because they have a similar amphipathic nature. What does amphipathic mean? One part's polar and one part's non-polar. So this steroid can slip right through the membrane because of this huge non-polar area, right? So it can hang out in the membrane. Remember, cholesterol is a part of your membrane, but what does it also have? Hydroxyl. What can the hydroxyl do? I have two lone pairs. These can interact as acceptors. This can be a donor. So draw a possible hydrogen bond. You just have to draw one. So if this is going to be an acceptor, let's draw a hydrogen. So we would have a hydrogen bond like that, right? But you could draw three. There are three possible. Yeah? Okay. So let's go see if we can get a couple of eye clicker points now that you know the whole thing. Okay, so get your eye clicker out. Give you all a second. Get your eye clicker out. Okay, y'all ready? You can have your notes. You can have your best friend. All right. Which relationship is inverse? When one increases, the other decreases. What relationship is inverse? Don't forget to either put your peas and vegetables on the table or use PIV-NERD. Remember when we talk about these kind of things? One of the two. Remember, I give you 1 minute. Okay, 3 seconds. That needs to click in. All right, so turn, talk to your neighbor. Turn and talk to your neighbor. So don't forget to check in again. Okay, 5 seconds. Okay. So you should have used PIV-NERD, and we said what relationship is inverse? Well, if I increase my pressure, this side of the equation has to be equal to this side of the equation. So then what has to happen to volume? Has to decrease. If I pick any variables that are on opposite sides of the equal sign, then it's going to be a proportional relationship rather than an inverse relationship. So you should have picked D. What'd you pick? D, yay. Okay, we went up, good. Okay, now you have to kind of think about it in a problem. We have a sample of gas in a 1 liter container. It is at 1 atm of pressure and it is placed into a larger container. What happens to the pressure? I would suggest Pivner with this one. Give you 1 minute. Ten seconds. Okay, turn and talk to the people around you. Everybody, don't forget to click in a second time, and y'all on chat, you can use the chat. Okay, 5 seconds. So what did you use? I suggested Pivner. So we put it into a larger container. What does that mean? Volume increase. So what happens to the pressure? It decreases because it has a inverse relationship. So pressure decreases. It's not increase, it's not stay the same, and it's not information is given. So it should be A. Good, good. Okay, I think that's all we have time for. Y'all study, please study. Don't forget, chapter 7 homework is due tomorrow night. I will see you all on Thursday for the exam. If you have any questions, please email me. Anybody on Zoom need anything? Anybody need anything? Okay.